There is a planet in our solar system that humanity has visited exactly once. We were there for about 6 hours. One spacecraft, one pass, one narrow window. And then it was gone forever into interstellar space. Nearly everything we believe about that world comes from those 6 hours. That planet is Uranus. And in 2024, a team of scientists went back through that decades-old data and realized something genuinely unsettling. We may have arrived on the single strangest day that planet experiences. Not a typical day, not even a slightly unusual one. A day so rare that it happens less than 5% of the time. Which means that for almost 40 years, much of what we've taught about Uranus may have been built on a fluke. But to understand why that matters, and why this quiet, pale, boring-looking planet is one of the most hostile and bizarre places in the solar system, we have to start at the beginning, because Uranus has been confusing us since the moment we found it. From Earth, Uranus barely registers. It's about 1.8 billion miles away, which is so far that it appears as nothing more than a faint smudge of light. For thousands of years, ancient skywatchers looked directly at it and saw a star. It was hiding in plain sight, catalogued and dismissed. Then in 1781, an amateur astronomer named William Herschel noticed something odd. This particular dot wasn't keeping pace with the sky. Night after night it drifted, slipping slightly behind the background stars. Stars don't do that. Planets do. Herschel had discovered the first new planet in recorded history. And because he found it, he got to name it. He chose Georgium Sidus, George's star, after King George III of England. You can guess how that landed outside of England. It did not catch on. The scientific community eventually settled on Uranus, after the Greek deity of the sky, making it the only major planet named from Greek rather than Roman mythology. But here's what people miss about that discovery. Before 1781, our known solar system ended at Saturn, roughly 890 million miles out. Uranus sits at about 1.8 billion. In a single night, the size of the known solar system effectively doubled. So astronomers pointed everything they had at it, and almost immediately, it started behaving in ways that made no sense. The first clue came from its moons. Over the following decades, observers picked out several large ones, but their orbits were wrong. Moons normally circle a planet's equator like a belt. Uranus's moons orbited almost vertically, looping up and over the planet instead of around its waist. There was only one reasonable explanation, and it was a strange one. The planet itself had to be tipped over. Today we know exactly how far. Uranus is tilted about 98 degrees from its orbital path. Every other planet spins more or less upright, like a top. Uranus is lying on its side, rolling around the sun like a bowling ball. And this creates a seasonal system unlike anywhere else we know of. Think of its 84-year orbit in 4 stages. In the first, one pole is aimed directly at the sun. That entire hemisphere sits in unbroken daylight for roughly 21 years straight. Meanwhile, the opposite hemisphere is in total darkness for exactly as long. Not night, not winter, 2 decades of continuous, uninterrupted dark. Then the planet rolls onward, and the geometry shifts. Now the sun is striking Uranus side on, and because the planet spins once every 17 hours, most of it experiences something almost familiar, a day and night cycle. Except the sun doesn't rise in the east. It rises in the north and sets in the south. A vertical day. Roll another quarter turn, and the hemisphere that spent 21 years in darkness swings into permanent light, while the other gets its own 2-decade night. Nothing else in our solar system works this way. And scientists ran the logic forward. A planet where entire regions cycle between decades of constant sunlight and decades of absolute darkness should be violently unstable. That kind of uneven heating is what drives weather. On paper, Uranus should be one of the stormiest places we know. So we looked, and every time we looked we saw nothing. A smooth, pale blue-green sphere. No bands, no visible storms, no structure at all. It looked less like a planet and more like a cue ball. Something wasn't adding up. And there was only one way to find out what. We had to go there. That was easier said than done. At nearly 2 billion miles out, Uranus was, for most of the 20th century, simply out of reach. Then in the mid-1960s, someone noticed a gift hiding in the calendar. Jupiter, Saturn, Uranus, and Neptune were about to line up in a configuration that occurs roughly every 175 years. With that alignment, a spacecraft could skim past each planet at exactly the right angle, steal a little of its orbital energy, and slingshot onward to the next. It's called a gravity assist, and it meant one probe could tour all four giants on a single tank of fuel. Missed the window, and the next chance wouldn't come until the 2150s. This became Voyager 2, launched in August of 1977. But just months before it left the ground, we learned something about Uranus that changed the entire mission. Earlier that year, astronomers were watching Uranus pass in front of a distant star, a standard way to measure a planet's atmosphere. As the star approached the planet's edge, it blinked. Several times, something invisible had crossed in front of it, and when the star emerged on the other side, it blinked again in an almost mirrored pattern. Uranus had rings. Nobody expected that. At the time, Saturn was thought to be the only ringed planet. But these were nothing like Saturn's broad, bright bands. Uranus's rings were dark as charcoal and impossibly thin, with sharp, clean edges. And that was a problem, because rings shouldn't behave that way. Ring particles all orbit at slightly different speeds. Over millions of years, they bump, jostle, and drift apart, spreading into a wide, diffuse disk. That's exactly why Saturn's rings are so broad. Uranus's weren't spreading. They stayed in tight, disciplined lanes, as if something was holding them there, and nobody could see what. Voyager 2 would have to answer that too. The spacecraft swung past Jupiter, then Saturn, and finally reached Uranus in January of 1986, nearly 9 years after launch. It passed within about 50,000 miles of the cloud tops. Right away, it started finding moons, 10 new ones, hiding in the dark, too small and too faint for any telescope on Earth. But one moon it already knew about stopped everyone cold: Miranda. Miranda is small, roughly 290 miles across. It should be a boring, cratered ball of ice. Instead, Voyager sent back images of a world that looked assembled from mismatched parts, with enormous chunks of wildly different terrain slammed together at hard angles, as if it had been shattered and rebuilt in a hurry. It also has the tallest known cliff in the solar system. Verona Rupes drops an estimated 12 miles straight down. The tallest cliff on Earth is barely 1, and because Miranda's gravity is so weak, stepping off that edge would mean falling for about 10 full minutes before you reach the bottom. Voyager also solved the ring mystery, and the answer was elegant. Tucked among the rings are tiny moons, some only a few miles wide, orbiting just inside and just outside each band. When a particle drifts inward, the inner moon nudges it back out, drift outward, and the outer moon tugs it back in. Between them, the ring gets squeezed into a razor-sharp lane and held there for hundreds of millions of years. We call them shepherd moons, because that's essentially the job. So the rings made sense, but the weather still didn't. Voyager confirmed the atmosphere is mostly hydrogen and helium with a meaningful amount of methane. And methane is what gives Uranus its color, absorbing red light and reflecting that blue-green back at us. What it did not find was drama. No great storms, no churning bands. The most extreme seasonal setup in the solar system was producing one of its calmest atmospheres. The explanation came down to heat. Specifically, the lack of it. Jupiter, Saturn, and even Neptune all radiate significantly more heat than they receive from the Sun. They have powerful internal engines, and that leftover heat from their formation is what fuels their storms. Uranus barely does this at all. Its internal heat output is remarkably low, which starves the atmosphere of the energy it needs to build big weather systems. Mystery solved. Cold inside, calm outside. Except that explanation immediately created a much bigger problem. Before the flyby, nobody knew whether Uranus even had a magnetic field. Jupiter and Saturn had them, so it seemed likely, but Uranus was clearly built differently. Voyager found one, and it was frankly a mess. On Earth, the magnetic field is generated deep in the core, where liquid metal churns around a solid iron center like an enormous natural generator. The result is tidy, poles that roughly line up with the geographic ones, and clean, symmetrical field lines. Uranus breaks all of that. Its field isn't centered in the planet. The source is offset by about a third of the planet's radius, and it's tilted roughly 59 degrees from the rotation axis, which is already knocked over by 98 degrees. So as Uranus rolls along, its entire magnetic environment wobbles and corkscrews through space. On Earth, auroras stay politely near the poles. On Uranus, they wander, showing up in unpredictable places as the field lurches around. Which raises an obvious question. If the core is too cold and too quiet to power a field like that, what's generating it? The answer is in the name we now use for this class of planet. Uranus isn't a gas giant like Jupiter or Saturn. It's an ice giant. And that word is deeply misleading. Beneath the atmosphere, Uranus is largely water, methane, and ammonia. But under the crushing pressure inside a planet that size, those materials behave like nothing in your kitchen. They're squeezed into a hot, dense, electrically conductive fluid, a superheated slush, thousands of degrees hot, under so much pressure it can't boil away. That churning layer sits relatively close to the surface compared to Earth's deep core, and as it moves, it generates the magnetic field. That's why the field is so lopsided. It isn't coming from a neat sphere at the center, but from a shallow, sloshing shell. Which brings us to the discovery that broke everyone's models. Planets with magnetic fields also have radiation belts, zones where charged particles get trapped and spiral back and forth at enormous speeds. Earth has them. Jupiter's are ferocious. Voyager found Uranus had them too, and they were staggeringly intense. For high-energy electrons, they ranked second only to Jupiter's, on a planet with a cold interior and a weak internal engine. That alone was strange. But the real contradiction came from the same instruments at the same moment. Radiation belts need fuel. Those particles come from plasma in the surrounding magnetic bubble, usually supplied by the planet's moons and atmosphere. For belts that powerful, the magnetosphere should have been full of it. It was nearly empty. Scientists were staring at a roaring fire with no visible fuel. It didn't match any model we had, and it cemented Uranus's reputation as the great oddball of the solar system, a planet that simply refused to obey the rules. That mystery sat unsolved for almost 40 years. Then in November of 2024, researchers at NASA's Jet Propulsion Laboratory did something clever. Instead of studying the 6 hours of flyby data, they examined the months of solar wind measurements Voyager took before it arrived. The sun constantly blows charged particles outward across the solar system, and normally a planet's magnetic field deflects them. But occasionally the sun throws a much heavier punch. What the team found was remarkable. In the days just before Voyager's arrival, the solar wind pressure at Uranus spiked to roughly 20 times what it had been shortly before. A powerful gust slammed into the planet and compressed its magnetic bubble dramatically, right as our one and only spacecraft came flying in. And that compression does two things at once. It squeezes plasma out of the magnetosphere, and it energizes electrons in the radiation belts. Empty magnetosphere, supercharged belts, the exact contradiction Voyager measured. The researchers estimate this compressed state occurs less than 5% of the time. If Voyager had shown up a few days earlier, it would have found a completely different planet. For 38 years, our entire picture of Uranus as a magnetic freak was built on a single measurement taken during a rare storm. And there's an encouraging twist. With the missing plasma explained, it's now plausible that Uranus's moons have been venting material into that bubble all along, which is exactly the kind of hint that suggests some of them may be geologically active and possibly hiding liquid water beneath their surfaces. We're still learning. In 2025, the James Webb Space Telescope spotted a moon only about 6 miles across that Voyager had flown right past without noticing, bringing the confirmed count to 29. And the community wants to go back. A dedicated Uranus orbiter with an atmospheric probe was ranked the highest priority flagship mission of the decade by the National Academy's Planetary Science Survey. It would put a spacecraft in orbit for years rather than hours, dropping a probe into the atmosphere to finally sample what's down there. Funding and plutonium supply have pushed the likely launch into the 2030s, with arrival in the 2040s. That's a long wait, but consider what we're waiting for. We've landed on Mars, orbited Saturn for 13 years, and flown through Jupiter's radiation. Uranus got 6 hours, on a bad day, and still overturned our understanding of how planets work. Ice giants were once thought to be rare oddities. We now know this size of planet is extremely common around other stars, which means the strange world sitting quietly in our own backyard may be our best model for a huge share of the planets in the galaxy. We looked at it once, for 6 hours, during a storm, and it's still the most misunderstood planet we know. Imagine what we find when we finally go back and watch it on an ordinary day.